So good morning, ladies and gentlemen. So I want to thank you first for inviting me to be here. So I want to thank Professor Zhang and another Professor Zhang, right? And also Professor Kim, Professor Chen, and also Professor Li for inviting me to be here. I'm still feeling a little bit jet lag, but I do like the Jeju Island. It's actually my second time to be here. I like the sea, the beach, and the food, the Korean barbecue, and of course the opportunity to talk to you about some of the work my group has been working in the past few years. So again, my name is Sikai Chen. As you can see from my lab logo, I direct the Sky Lab. Maybe the word is too small, so my lab's focus is on human-centered AI and transportation, which is also the main topic for today's presentation. So we are going to have two presentations. The part one will be focusing on multi-agent cooperative driving automation. And also the second one, we're going to talk about the digital twin-enabled interactive autonomy. So without further ado, we can get started. I always like to begin with these slides, talking about the big problems in transportation. So as you can see, a lot of fuel cost, the extra time spent on the road, and put a lot of economic burden to every single commuter. When you look at the cost, we have the work zone related congestion, we have the bottleneck, and another very important thing is the traffic incident. If you look at the number, every single year there are more than 1 million people die in the entire world. And even in the well-developed country like the US, every single year there are more than 40,000 people die. So this is a huge issue that really shattered the family very quickly and put a lot of burden to the society and people's life. So this really gave us a motivation to look at the new technologies, including the vehicle connectivity and vehicle automation that you may probably know. The US DOT from about 20-some years ago started to look at this new technology, the connectivity. The key idea is that the connected vehicle will talk to each other and also talk to the infrastructure, talk to the pedestrian. So now we all carry our phone, right, the smartphone, and then you can connect through the cellular data. The hope for the vehicle is that with this shared information through connectivity, we hope the driver can make better informed driving decisions. But the reality is not going as we intended to go, because there are lots of studies showing that this connectivity itself won't work well. One of the reasons is that there are lots of uncertainty in human drivers' behavior. Maybe the unwillingness to follow the instruction being sent to them, right? So you're driving and then you receive a message telling you should drive slower. How many people will actually follow without law enforcement? And some research even argue that it may not be the reason that people don't want to follow this instruction, but it's just impossible. So imagine you are driving your vehicle and then you have a screen, and on the screen it shows the location of the surrounding vehicle and then a lot of numbers indicating their speed, acceleration, and all these numbers are keep changing over time in real time. How you're going to use that information. So that is why the autonomous vehicle or autonomous driving come into play. The good part about autonomous driving is that you can use AI and intelligent control to precisely control the vehicle's movement. If you ask a human driver to drive, let's say, 30 miles per hour, the driver may drive from 20 to all the way up to 40, 45, or even more. So you see the uncertainty or the unwillingness to follow the speed limit. But if you ask an autonomous vehicle to do so, it will do it very precisely. But autonomous vehicle also has its own problem. If we look at this video, you can see that the car is very slow and even slower than the person riding the bike there, which is not necessarily a bad thing due to safety concern. But in some other situation, this behavior, very conservative behavior, may not be ideal. I read the news a few years back about an Uber vehicle when Uber still had its autonomous driving team before those fatality crashes. The Uber vehicle was very hesitated to merge into a highway segment because the surrounding vehicle are not willing to give the right of way to the Uber vehicle. So due to safety concern, the Uber vehicle cannot merge in. And that was because of the lack of communication. So that's why it's important to that people start to start that to put this connectivity and automation together. So we have the connected and autonomous vehicle, which is part of the main focus on in this presentation. So we have the technology called the Cooperative Driving Automation, the CDA. This is actually a name that US DOT started to use from about 10 years ago. Basically, with the shared information and intelligent control for multiple vehicles, we hope the vehicle can work together, not only among the vehicle, but also with the infrastructure. So we'll look at this figure on the right. This vehicle can form a pretty tight fleet. For normal vehicles, you need to basically keep about 1.5 second time gap or time headway between each other. But with the shared information and precise control through AI, we can reduce this time gap or time headway to as small as maybe 0.4 seconds. 0.4, yes. And that really increases the roadway capacity a lot and, of course, bring other benefits like the safety. So something else about the background. So to do this intelligent control or for CEA, there are in general two types of AI in terms of learning. So my research basically use these two. The first one is imitation learning. This is pretty easy to explain. So basically, you collect data from human driver. You get data about what situation they are dealing with, and in the meantime, what decision they're gonna take when dealing with this situation. So you gather this information, and then you create a neural network or a machine learning model that try to map your input with output to action, which is the driving direction. The good part and for the autonomous, for imitation learning is that this type of thing is easier to design and relatively easier to train compared to the other methods that we'll introduce in a few seconds. But the downside is that you really need good data. If you collect data from bad drivers, then it's like garbage in, garbage out, right? And also, it's hard to find those dangers or corner cases where you can actually use that to train the imitation learning. And in addition to those, because the imitation learning not directly trying to learn the best possible driving strategy, but it's like learns from human driver. So it may be only able to perform as good as the driver you collect data from, but not be able to do a better job. So those are the downside. Another type of learning is reinforcement learning. You may heard about this. There are many applications using the reinforcement learning to show that they outperform top professional human players. One of the most famous cases is AlphaGo in 2016 when it outperformed got 60 straight wins against top professional human players, including the world champions in Korea and also in China. So for the driving, basically, the AI agent is able to interact with environment through the trial and error. This process is very close to, or very similar to how we as humans learn to do certain stuff. So basically, when you learn to do a new task, right, and then you take some actions, and then your supervisor, your advisor, or your friend, your parents will give you some feedback. That's the reward signal you are receiving in this step, one data point. You're going to combine that with all the past experience, the previous data point. You put them together and try to analyze them, and with a goal of improving in long term. So here the AI will be doing a similar thing through the reinforcement learning. Receive a signal, and then collect the data, and then the loop will be keep going. But the bad part for this type of learning is that it's generally harder to design and to converge. But as we mentioned, if we can do it well, it really has the potential to outperform human drivers in all those driving tasks. So with those as with the background, I'm going to introduce you 3 examples about some of the work my team had been working on. Starting from the first one, developing innovative AI for multi-agent system. So in the future roles, there will be this type of two type of cars. Some of them will be this white one, so the human drivers like what we have right now, and we are also going to have the autonomous vehicle like this red and also blue one. For the autonomous vehicle, they can capture the information about the surrounding vehicle, like their driving speed, driving direction, location, and so on. And through the connectivity feature, they're gonna able to share this information with other connected vehicle in this network. And then our goal is to design good CDA control using AI or other method to make decisions for the controllable agent, which is the CVs, to improve the traffic. But achieving a good CDA is not an easy task. So I listed a few here, a few challenges. There should be more. First is a highly dynamic mixed traffic environment. So if you think about it, all these vehicle location, driving direction, speed, acceleration will be changing over time in real time. And the human driver will create lots of uncertainty, so sometimes you just don't even know what they're going to do. The second challenge, I call that dynamic number agent problem. Basically, right now you see 7 human-driven vehicles and then 2 CVs in this network. But as we go, a few seconds later, you're going to see some vehicle will join the network, some vehicle will goes out, right? So maybe 5 seconds later, there are 4 human-driven vehicles and 3 autonomous vehicles. So the number of the agent is also keep changing over time in real time. But for most of the control or machine learning algorithm, you require the input and output size to be a fixed number rather than dynamic. You can think about this in another way. How many of you have experience in like regression? Regression analysis or, yeah, right. So you cannot build a model that at this moment you have 10 independent variables, but then 3 seconds later, you're going to have only 2 independent variables. And then not considering their location also change, so their relationship also change. So that also leads to the third point. These agents are also going to interact. They're not independent to each other. So how you're going to consider what information I should consider. So if I'm driving this vehicle, am I going to consider this vehicle or that vehicle? How should I weight their importance, right? So that's why I proposed my team. My team is proposed to use a method called graph representation. So basically, we describe this information flow topology using a graph. Pretty intuitive. So we have the white dot represent the human driver, HDV, blue dot the CAV. So the local link between the white and blue dots are the information you get through your onboard sensor of the like CAV. And then the CV will send this information to other CV in this network. So through this graph representation, we can find a way to intuitively reduce the number of parameters in the machine learning. So that is, as you may know, that is always a problem that when we have a large number of parameters, then it's likely to overfit or stay in local minimum or local optimal. And if we combine that with reinforcement learning, it's going to be a mess. So on top of this graph representation, we add on reinforcement learning. So in this case, a simple deep Q learning. So we created what we call the graph convolutional Q network. I'm going to skip the detail, but basically this is specifically designed to take care of the dynamic number agent problem and complex interaction among the agents. So we have a simple demonstration motivated by the Uber example that we talked about in the early slides, where it was hard for the vehicle to merge in or merge out. So here we have 2 types of CVs. The red one wants to merge out on the first ramp, while the green one wants to merge out on the second ramp. And we also have the background human drivers. So, okay, for our GCQ AI case, you're going to see that this green CV knows the intention of the red one, so it moves out from the very right lane to create some space for the red one to merge out on the first ramp. So you see no congestions. But for the other rule-based case, I think it's going to be played. Okay, so you can see congestion will accumulate very fast because this vehicle, they only know their own intention. They don't know what other vehicle wanted to do. And yeah, so they run into a problem like that very quickly. And this result basically shows the cumulative reward. The higher the bar, the better the performance. Our AI-enabled case indicated by this blue bar, you can see they're better than other models we find in the literature. But the standard deviation of our method is very, very small, indicating that they consistently perform well. The x-axis here is different traffic density, so you can consider that as a different market penetration as well. So moving on to example 2, mitigating highway congestion in a mixed traffic stream using CEVs. I guess we all have experience like that. So in the morning, I was talking to Professor Cho. It seems that his tour yesterday was not so, no, it could be better. So Professor Chen said it can be improved because of traffic congestion. How many of you drive? Okay, I see some hands. Basically, you're gonna see that sometimes when you are driving, other driver may all of a sudden cut into your lane for no reasons, right? And if you think more about that, are they gonna be driving really faster by doing that? Probably not, right? So this kind of tells you that human drivers' behavior are intrinsically, or it could be intrinsically irrational. Because they have limited information. They can only see that far away. Okay, I have a gap over there. Maybe I can drive a bit faster. But they have no idea about what's happening in the downstream. So they are doing this. And this lane change will create this stop and go wave. And then that will create lots of problems in energy consumption, safety, and also in shock wave propagation. That can actually carry on these issues even away from this region to other regions to create more problem, right? So researchers have been working on this active traffic management, ATM strategies, like speed harmonization, variable speed limit, and ramp metering. But all these strategies requires human drivers' compliance. If you are asking a driver to reduce his or her speed, he or she may not follow. But later on, if we use the CEV, we can do this pretty well. So I want to start with a video, a very famous research done by a Japanese researcher, Dr. Sugiyama, also from about 20 years ago. You see there are lots of research, classic research from 20 years ago. So so initially, these vehicles are equally gapped, right? So as you may imagine, if they all drive at the same speed, theoretically, they can keep going forever without any traffic congestion. But some drivers, they see a gap in front of them. They want to drive faster, so they accelerate to try to close the gap so that the driver behind them follow. So the driver behind them follow. But then when they start to realize, oh, I'm too close to the vehicle in front, I may need to take a sharp break. And so the vehicle behind them follow, so the vehicle behind them follow the same thing. Sometimes they even need to make a full stop. And apparently the traffic is very bad starting from this point. And the idea of using CEV to mitigate this congestion is that when we have a CEV in the traffic stream, so now we are not considering the lane changing behavior. When the leading vehicle is somehow need to slow down for whatever reason, my CEV will capture this quick enough through the onboard sensor and analyze this quickly and also send this information to other CEV in this string. So they can control their speed in a smarter way to dampen this shock wave. So a simple video we made to illustrate. Basically, the leading vehicle somehow sudden brake. You see the light. I hope you can see the light of this red CEV is on compared to the human-driven vehicle, indicating that this vehicle will slow down faster, but not as hard as the human driver, right? And this is, oh, sorry. I guess I have to play that video again. Yeah, so I'll use this opportunity to drink some tea. Yeah, so, but the second part of the video basically tells the same story, but it's just visually, you can see more vehicles and doing some benefit for a larger vehicle string. Yeah, so the leading vehicle takes sudden brake, and this is how it looks like when we have multiple vehicles. Right. So that's the main idea for the non-bottleneck related congestion. But for the bottleneck related congestion, you see there's a physical bottleneck on the right. So lane changing will be involved, creating those sharp brake and stop and go wave. Our AI-enabled case down below, you see that there are several red vehicles controlled by the AI. After analyzing the situation through those graph representation and so on, you see that they decided to work together to kind of form a queuing system to control the inflow rate of HDV flowing into this bottleneck. So what it does is, instead of having a large congested region like what you saw on the top, the AI is able to break it down into two less congested regions. And also indicated by this blue bar, the AI-enabled case. The overall traffic throughput is higher compared to the VSL or other method that we found in the literature. Example 3, collision avoidance framework for CAV under crash imminent situations. We had a graduate student at Purdue, one was still at Purdue, Mr. Trevor Moore, driving on the road, not wearing the seatbelt. Don't do this. Also playing with his phone. Please also don't do that. And when he was right up to hit the vehicle in front, he decided to take a sharp turn. And there was actually another sharp vehicle on the side. I hope you did see that. I think we can all agree that this is very, very dangerous because this side swipe may lead to a series of collisions that involve multiple vehicles in the area. But by the way, I assure you that is not how Trevor drives in real world. We ask him to intentionally to do that. So the literature shows that there are about 95% of all the roadway crashes are directly or indirectly related to human error. There was a survey, and then people said, okay, about 88% of the drivers think themselves are good or even excellent drivers. But if you consider almost all the crashes are due to human driver, there could be some overconfidence. I'm not sure if you heard about a term called risk compensation. It's a pretty famous term in the AAP, the statistical field. Professor Mannering started to use this word. Basically, it tells you that for people with very good driving skills, then those drivers may feel safe of doing other tasks like playing with their phone or listen to the music. I'm not saying you shouldn't listen to the music, but it's sort of a distraction. So this overconfidence may actually lead to higher crash in some cases because there are overconfidence. And of course, there are other factors such as fatigue or slow reaction time. So most of the researchers think that the major benefit bring by this autonomous driving is that we hope to significantly reduce or even completely eliminate human error from the road. But the transition period will be very long. So some researchers think there could be, maybe let me do a quick survey. Professor Kitai, when do you think the driver will, we can reach a 100% market penetration? In how many years? Like a guess. Yeah, yeah. That's why I always tell the student that this is your work, because we are probably too old for this. We may not even see this, but then you will be the researcher where people actually use the vehicle, use the technology. So, and then you can actually change the technology that we will be using. So lifetime, we have one data point. And Professor Cho, what's your opinion? Oh, never? Professor Jin Wu? It depends, yeah. I think that is the correct answer. It depends. And Professor Chen, what's your opinion? Yeah, 20 years, 30 years, 50 years, yeah. So you see that I think we as researchers are too conservative. Yeah. If I'm asking this question to some young people, they may say like 10 years or 20. But there will be a long transition period where both CVs and HDV were on the road in the same time. And actually, I personally think it's never going to be 100% market penetration because there's nothing wrong that you just drive on the road, right? Because you don't only use your car for commuting to work. Some people, they just like to drive. There's nothing wrong about that. And also, some people may never trust to give their life or control to a machine, no matter how good it is, right? So there will be two perspectives when there's a mixed traffic. The first one is autonomous vehicle will be at fault. This is pretty self-explanatory. Reasons like software failure or mechanical issue may have the vehicle to malfunction, and this by natural receive a lot of attention from all the researchers, engineers, and the AV manufacturers. But what we saw in Trevor's case is perspective two. This is not so emphasized right now. You may find more opportunities there. The AV is not at fault, but there could be aggressive human driver in the mixed traffic, and then they are creating problem, but the AV are not able to dodge that, right? So in order to help with something about the perspective two, we are doing this. CDA, Trevor is driving this yellow vehicle. I didn't show you the right side. You didn't see a crash. That's what happened. Trevor turning aggressively, these three CVs work together, sharing information. One blue car accelerate, one decelerate, all done by the AI. So they dodge the crash collaboratively. We consider two types of collision avoidance. Deceleration only or deceleration plus lane changing. The deceleration only case means there's no additional lane, or in the additional lane there's no CEV. There's nothing we can do about it. We can only decelerate this red vehicle. But the success rates are very low, all smaller than 40% in some cases, or even close to 0%, because this following human driver may have a slow reaction time. It's not his fault or her fault, by the way. It's just not enough time to react, so a secondary rear-end collision. But when we enable the information sharing through connectivity and then the cooperative driving automation, AI, we can significantly increase the successful dodge rate to more than 60%, which in cases that are not so severe, even close to 100%. Some simple demo is in a hallway when I was still at Purdue, having my team doing research there. I'm not going to show the detail because there are many things not working so well. But basically, we are testing if we can have one vehicle decelerate or move to another lane using the control algorithm that we built. So what's about the future? Those are the work that we did in the domain of CDA. So basically, we are talking about here, multi-agent control. So collaborative sensing, cooperative automation, multi-agent control, mainly for AI and CV, but later on, you can extend that to eco-driving with smart infrastructure like the keynote speaker, Professor Lee was mentioning. In short term, we can keep improving this multi-agent, right? So we were using graph representation. You may use something else. New technology will come out. New algorithm will come out. You build new stuff. And through this process, we want to understand, maybe not we, but also all of you guys, we can try to understand the individual role of this AI or intelligent control. So you kind of have a flavor already, I hope, at this point. There will be multiple systems working in the same time. Some system will be doing the lane keeping. Some system will be talking to other vehicle, collaborative dodge for the aggressive driver. How are should they work together? So long term, it's like we are running a company or all the universities, right? So we have the president, the dean, all the researchers, the department head. So they have a structure. So AI should also have a structure. Some decision will be made at high level. Some decision will be made at very local level. So we need to establish some sort of structure. Then we can scale them up. Right? That's what I think. That could be wrong. Don't take this, just some thought. So some example along the line that I'm thinking. For example, we have example about bottleneck, non-bottleneck congestion. What if we are going to combine them, right? So we can have a simple network or system like this. You have the stop and go drive, but you also have the lane changing. Some vehicle will be get into the system or get out. For some reason, this word overlap. I hope it won't affect. Also, we can simulate how we are going to gather this information, maybe through direct vehicle connectivity, but maybe through the roadside unit. You put some roadside unit here, gather information for the passing vehicle, send the information to CAV. So there could be information delay, sensor error. We can simulate all those kind of things and see their system level impact. And you can think about some other things. So one AI could be doing traffic stabilization, but there can be another AI deciding when to release an autonomous vehicle into the system. Thinking about you're a director of a traffic police department, right? So you have 10 autonomous vehicles you can send into the traffic. The decision is when to send the vehicle into the system because you have limited resource, and when to take them back. So you can reuse them later on when you expect something bad will happen. So some flavor, there will be collaboration between AI. Long-term city level, this is actually a work that we published with Professor Chen and some of the Hong Kong collaborators. City level, right? So some information will be processed as the cloud, high-level decision. But if you go down, there will be individual system at the vehicle level doing car following, lane keeping, etc. You can consider data fusion, flows, latency, all those things, and different type of computing, and also trade-off for the accuracy and then the speed. When you have a huge amount of agent that you need to make the decision for. The case that, another slide. So basically, you may heard about the term fog, cloud, fog, edge computing. On cloud level, you may process information about, maybe you are a city mayor. So you are thinking, in the next 20 minutes, there are going to be a peak hour. So my AI or all my smart agents need to shift from energy consumption to increase mobility. So that should be my focus. But then 20 minutes later, you don't really care too much about the traffic jam. Maybe you want the system to go back to consider the energy consumption. And then some local decision will need to be made at the fog level. So different fog areas doing the CDA within their own area. But then for tasks like lane keeping, you don't want the cloud to compute that. Take 10 seconds and tell you how your vehicle should drive in the next seconds. For lane keeping, you need high frequency of computing, right? Probably 10 times a second. You don't want to wait for the cloud to tell you. But for those higher level decisions, you don't need to really update them in real time. So some structure. For the work that we published, we are using an area from the city of New York in the Manhattan area, about 6 square kilometers. And we divided that into 6 fog areas. People were questioning us why we are doing that. We just try to show this framework work. And I'm going to skip all the detail and then show you a video we made without even mentioning how we set it up. Basically, we have 2 types of vehicle. The green one is AI-enabled rerouting vehicle. So they can talk to each other, talk to the roadside unit, like basically the fog node. So they have the bigger picture. Our goal is to create some traffic jam. Maybe you can think about them, some accident happened, totally block the road network. We want to see if our AI are able to learn how to dodge those. When we don't have the fog and cloud architecture, after about 1 week, 1 full week of training, reinforcement learning, it didn't learn anything because we are making routing decisions for hundreds of vehicles. You can consider the large space for reinforcement learning. It's just crazy. But when we have this cloud and fog architecture with only about 2 or 3 days, you barely see any AI-enabled rerouting vehicle get stuck on the road network. So that's an example. We haven't touched this part so far. That will be mainly the second lecture. The main thing is that for whatever AI we build, we need to make sure that humans trust the AI, so they are willing to use that. And also, people are talking about changing the infrastructure. The lane can be narrower, shorter. Maybe we don't need that. The stopping side, the distance can be shorter. But maybe the driver sitting in the vehicle will not feel comfortable about that, right? So there will be some reaction acceptance issue. And then the last thing, change in behavior, talking about the intelligent vehicle with the human users. When I present the crash avoidance framework to other people, one question I always receive is that, oh, do you think that will work in the real world, like the crash avoidance? How many of you think that will work? No? Oh, but you should still cite my paper. One thing that I always receive as comment is that your system will work well when people don't know the system exists. What happens if you know your surrounding vehicle will work together and dodge you? Basically, you're encouraging aggressive lane changing. And then that will create a mess. And then when people are comfortable with aggressive lane changing, all of a sudden, the vehicle beside him is not an autonomous driving vehicle. There will be more crash. But that question is too hard for me to answer, so I'll leave it to you guys to think about it in the future. So next lecture, we will be talking about human-centered design computing. Here is a reference list basically about all the work we did in this presentation. I want to also use this chance to acknowledge our sponsor, the US DOT and the Wisconsin Department of Transportation, and of course, WRF, the Wisconsin Alumni Research Foundation, and my college. And also my team at the Sikai Lab. I really have the privilege to work with all the talented students and postdocs. What happened? So all the work you saw today are all teamwork. And without their talent and dedication, there's no way we can come to this far. So it's my privilege to introduce them to you, and thank you very much for your attention. I would like to take any questions or comments that you may have.
Do we have any questions?
Good morning, Professor, and thank you for your great presentation. And I assume you know a PhD student under Professor Teza in ICE. And your studies on mixed traffic of CAVs and human driving vehicles are very interesting for me. And I have a question about the simulation validation process in examples 1 and 2. So how did you set up the lane change models for CAVs and HDVs? And were the same models applied to both types of the vehicles? And additionally, I am curious about your opinion on how the interactions between vehicles, like lane changing near bottleneck or after congestion, can be considered in mixed traffic scenarios.
Can I repeat? Maybe I'll answer the first one, and then I think I lose part of the second one. So the first one is actually a very, very good question. We run into that problem a lot. We did a lot of search in the literature. So you're talking about what's the model we used, or how to evaluate that in terms of the lane changing, right? For human driver or for the CV. Let's talk about this first. So the background vehicle are all human driven vehicle, and basically we were using the Sumo in this case. Yeah, so in Sumo, there are some built-in functions for the lane changing. And I always had that question when my team is doing this, when myself is doing this. What is the basis of those lane changing model? In short, I don't have an answer for that. That's what most other researchers are using. So there are, if you look at the Sumo document or WISM document, they're going to talk about the model's name, but it's very hard for you to find detailed information on that. And then that becomes a very common thing for the paper publication, right? So I think when we have on Monday the keynote speech, right? So many professors were talking about their experience in publishing top journals. What I did is I went to those top journals and I see if I can find any information on that. And I went to conference, talked to top professors in this field. My summary is that maybe I haven't talked to enough people, so just as a disclaimer. But for most of the people I talked to, we kind of have an agreement that there's currently not a very good lane changing model. So that is something that we should build. So for the background human driven vehicle. So they're going to use some rule-based vehicle. So basically considering the time gap, the headway between between vehicle 1 and then the following vehicle. And then when the headway is within certain threshold, when their speed is within certain threshold, they're going to do the lane changing. And what's the basis on that? I don't know. So that is for the background vehicle lane changing. But then I guess you start to have some thought about this lane changing is not an easy thing. Even defining one good lane changing model is hard. How about I know what you want to do, you know what I want to do, then there are so many other vehicles driving around me, then when we're going to change the lane, that's a very complicated decision making. So that's why we have this AI to kind of optimize for a centralized goal to improve the traffic, but in the meantime satisfies individual vehicles' intention. I hope I did answer your question. So what was the second question, sorry?
Near bottleneck or the extra transistor, how do you think about the interaction between these? Because in free flow and extra transistor, their interactions can be different. So I want to listen to your opinion.
Yeah. The intention shift, you mean before or after congestion? As a driver? Between two cars. Yeah, again, I think this is a very hard problem. So the reason I was asking how many of you drive is because driver kind of have a better mood when it's free flow. And then when you are starting to interact with other drivers, I don't think people can, oh no, I shouldn't put it in this way, but some people may start to take this personal. I want to drive faster than you because you overtake me a few seconds back, right? Did you run into those problems? Yeah, I think it's pretty common in the real world. So I think to quantify, in order to answer your question from a research perspective, I can say it's a very complicated question because to me, it's very hard to formulate that question mathematically or quantitatively. Yeah, but I guess there will be two steps. First, you need to think about how to formulate them, quantify them, and then think about how to model them. And then you need to support your finding from maybe a driving simulator study. Yeah. But to me, I think driver will change to a better mood when they're getting out of traffic congestion. So their behavior could be less aggressive compared to when they are in the congested region. Yeah, thank you very much. All very good questions.
Other questions?
I have one question about the reinforcement learning framework you mentioned. The reward is the objective of the agent. And how do you set the reward in your framework? Is that the benefit for only the car you controlled or for other system?
Yes. Yeah, thank you. So let's just use this as an example. So the cumulative reward is these bars. You have some background, so I think I'm going to skip that. so this reward is a combination of multiple factors. So we are evaluating by first their successful rate for these red and green CVs to merge out on their intended ramp within a given period of time. If they cannot successfully merge out, then our bar will be slower. So that is one component. The other component is the overall throughput. So we don't really optimize for individual cars. So but we kind of in favor of those CVs because if they failed, then this whole simulation will receive a very low score. So the overall performance. Yeah. But there are multiple ways to set this up. So that's why when you write a reinforcement learning paper, you need to do some sensitivity analysis. So you try and error not only the structure of your deep neural network, but also the weight you put. You need to tune in a reward function as well to see if you get your intended behavior. That is actually, to me, a big problem in applying RL to transportation problem because people will value things differently. So that's why in the second lecture, you're going to see we have some thought on that, and sometimes we don't use reward function in the RL. So I'm going to talk more in the second lecture.
Okay, thank you.
Yeah, thank you.
More question.
Thank you for your great presentation, Professor. May I ask a question about the future direction short term? I want to know more opinions or insights about the limitations of current multi-agent algorithm. It overall works well, but still have some potential hazard when collaborate with human or under some specific scenario. I want to know more about the limitation.
Right. I think we need the human in the loop. So for now, it's not the human in the loop. So that's why the second part is we're going to talk about something about human in the loop. Right. So how to, we didn't do a lot, but we start to think about that. So I think we are in the same line. So human in the loop, RL is one thing. And another thing, so as I mentioned, probably I should have spent more time here. For most of the research paper, I observed that nobody really find a systematic way to simulate. I should avoid making this strong statement, but many research haven't have a systematic way to simulate the package loss. So we are imagining. So for whatever you saw in my presentation, that's my limitation too. So other vehicle gets the information from other vehicles instantaneously, but this is not realistic. So there should be information loss. There should be latency. So is your AI still robust enough in dealing with those latency? So methodology-wise, whenever there's a new method come out, you can try to test it out. But the key point is that you need to apply them in a meaningful way. I think as transportation researchers, what we shouldn't do is just grab a new method and apply and see a better result. I think Professor Li Jun mentioned that in the keynote speech. I agree with him because that's not a major contribution. You need to think about this question in a more systematic way. So if you want to apply a new method, that is fine, but there should be a good reason. So the reason we are using graph representation because it reduces the number of deep learning parameters in a meaningful way. So we can expect the behavior happening. So that's our assumption. And then through the simulation, we validated that. Yeah, so thank you.
Thank you for your answer.
I also have a question. The CAV car means the connected vehicle, and I want to know why divided it into level 2 and level 3, because level 2 is still controlled by the human driver, but he can get the information. But level 3 is autonomous, and he just do the decision by the vehicle itself.
Right.
Yeah,
you mean you want to know what level we are using?
I want to know why the professor didn't divide the CAV into two parts.
Oh. You mean me or other people?
I mean you, yeah.
Yeah, that's a limitation. Right. I guess since for level 2, right, so you can have adaptive cruise control or some system like that. Then in the traffic stabilization, when you don't have the lane changing, I think if we don't need the human intervention, then there's no big difference between level 2 or level 3. Because in level 3, it may involve a more complicated automation function. And since when we use our RL, we are only controlling the longitudinal speed. So in that sense, we don't really need to differentiate them. I guess your question, and then the question becomes, when do we need to differentiate them?
Yeah.
If I can put it in this way. I guess it's coming back to what I mentioned. When you start to when you know specifically what you want from the human driver, right? So are they gonna control their wheel, but let their speed control done by a L2 vehicle? Or are they gonna have their hand off the wheel, but they need to be ready to take over? Or is your research don't even need to consider human intervention? So in that case, I think you need to start to differentiate level 2, 3, and 4.
Okay, thank you.
Yeah, thank you.